Woo. Here you have it, the B18C1 GSR block with the unfortunate rod knock. It's here inside our engine build room. We're gonna spec it out, see what it needs, see what we can salvage, and move forward from there. We'll inspect the oil pump later, but honestly, it's feeling seized already. Should be able to turn the oil pump by hand coming out, but there's probably a lot of particulates already stuck in this thing. So we'll tear this apart and find out how it looks. Either way, we're gonna get a new one anyway.
Alright, I'm just gonna voice over here to avoid listening to myself grunt and moan over breaking these bolts loose. They are quite tight. But yeah, we use a snap-on torque wrench in order to just see how consistent these tightening sequences were from prior assembly. And so far, it all looks pretty consistent.
Whew. Smells spicy. Woo. Definitely particulate recirculation. You see a lot of pitting. A good amount of pitting in the bearing. You can see here that there's some scoring. So whenever you have contamination, or if your engine doesn't break in properly, you have a lot of particulate still recirculating. What happens is it goes in through the oil pump, and sometimes oil filter doesn't catch it all because it's just so messy inside the rotating assembly. It ends up lodging into these crevices and making its way into the main bearing journals and even the connecting rod bearing journals. And what that does, it just creates a lot of contamination of hard, solid particulates, then creating some scoring, and really chews up the bearing, and then eventually chews up the crankshaft journals. This one's not so bad. You can see here. I'll show you an up close and personal. We'll see if we will. Ooh, yep. Just as I thought. You can see here how there's some pitting inside the bearings. And then some actual rubbing on this main right here. But you could even see more on the main caps, where there's some hard scoring here. This is a big gouge right here, which is exposing the copper from beneath. Definitely gouging from particulate contamination and recirculation. You can see that. So, yeah, definitely what it is, unfortunately, but this is where we're at. Feels really grimy. And this is the particulate recirculation that I'm talking about. So whatever breaks loose inside the engine, there's only a screen that filters the oil right before the oil pump. It's not really a element filter for various reasons, but whenever things break loose and get chewed up, it'll just chew up the oil pump itself. And then what happens in some cases, it could get this relief valve stuck open because that little piece of metal will just lodge in there and keep it where whenever it's relieving pressure, it'll open. But if there's a piece that's there, it won't allow it to shut to build pressure back up and then cause bearing failure in the long run, or if not, immediately. Some scoring here. Either way, usually we would spec this out, but in this case, we're probably just gonna get a new one. And we're still gonna spec out the new one, but you can hear that grime. Really gritty. Should be a smooth oil pump here, but this is definitely not a smooth oil pump. Ah, look at it, stuck.
As you see here, we're using a 1-inch standard for this micrometer. You're gonna always want to use a standard before using a mechanical micrometer. The standard will help you make sure that it's zeroed out and calibrated properly before measuring any parts. And you can see here that it's definitely calibrated properly while the two zeros are lined up. So now that that's checked out, I usually mic my way down to the bad journal just to make sure that everything that seems to be good is actually within expected specification. Yep, this one sure looks well below spec. Clearly, I mean, it's quite obvious, but you still want to know where it's at so that we can see if it's even possible to salvage this crankshaft. Even if I were to be able to salvage this crankshaft, I probably would avoid using it on this build since we plan on making some power out of it. On an engine that is spiritedly driven or performance oriented, I would avoid trying to save crankshafts only because of how high they rev and how much abuse they get. I usually want to use a new or a really good condition crankshaft after balancing and speccing out. Moving on to bore gauging. We have the micrometer set to 81 millimeters, or in other words, 3.189 inches. We use the bore gauge to pretty much set to 0 while it's fixed on the 3.189 inches. We're there right at 0. And then we're going to take it to the cylinder block and just measure the difference between the 3.189 inches and where the block is at in order to determine how much wider we need to go with pistons. Now, while prepping for assembly with new pistons, you're going to want to measure the piston's actual diameter in order to properly achieve piston-to-wall clearance. But in this case, I simply just want to see how the cylinders look right now in order to judge what size pistons I'm going to run with. And so far, it looks like we can go to the next step up, which is typically 10,000ths or quarter millimeter oversized. And the reason of going oversized is that currently the piston-to-wall clearance is reading about 2.5 thousandths, and we usually want to target 3 thousandths of an inch between piston to wall. And getting oversized pistons just gives us a little bit more insurance for us to achieve a perfectly straight cylinder wall without running into any low spots. And now that we have all of our preliminary measurements, we can go ahead and get the necessary parts. Then we'll move on to machining and then final assembly.